Okay, today we are learning about something known as electron configurations. Okay, what an electron configuration is an electron configuration tells us the location of the electrons inside of an atom. Okay, the location of the electrons inside an atom. The way I think about it is it's kind of like the address for the electrons or their location in a hotel. Okay, so I'm going to kind of use a little abstract analogy to help us connect to this concept because I found it can be helpful for students because we are getting very, very subatomic today. Okay, so most of the time when we think of atoms, right, this is the way we think about them. I mean, this is the way we learn them. General chemistry students make these models of them. Hard part is this is quite wrong in what an atom actually is. There's a lot more to these electrons than what these models show, which is maybe why we still model it this way, because it's really hard to show that. But this is kind of how we're thinking of it, okay? So I'm going to make the analogy that an atom is like a hotel, okay? Inside a hotel, hotels have different floors, right? In our atom hotel, we're going to call, whoa, I almost wrote on the board with a Sharpie. Get rid of that one. Where'd my black one go?
It's got in the water.
Oh, thank you. Okay, so inside an atom, we have what are known as energy levels. For analogy's sake, we're going to say those energy levels are like the floors of our hotel. Okay? Then, on each floor of a hotel, you have different rooms. Whoops. Inside the atom, these rooms are called subshells. Okay? So when a little electron comes to check into the hotel, right, they'll tell them, okay, go to this floor and go to this room. Just like you would in a normal hotel. Now, this hotel is really unique because not only are they going to tell the electron what floor and what room they're in, but they're also going to designate beds inside the room. Okay? So the next classification is inside subshells are orbitals. Okay, so once again, we're going like quantum realm here almost, okay? We got floors. Inside the floors are rooms. Inside the rooms are orbitals. For my analogy's sake, I'm going to call these orbitals bunk beds. This is a very cool hotel. It has bunk beds. But it fits the analogy well. Okay? So they're going to tell the electron, say, okay, go to this floor, go to this room, go to this bunk bed, and then they're going to tell them to sleep on either the top or bottom bunk. Okay? And this is known as the spin of the electron. And those are all the components of an electron configuration. So once again, this lovely model only shows us what part of it? Just the energy levels. The floors is the only thing this shows. There's so much more to an atom than just this, right? Inside of each of these are subshells. Inside of those are orbitals, and then inside of those orbitals are electrons, and they're spinning. Okay? All right, hang on for the ride. Here we go. Now, with our hotel, there are 3 rules that electrons always follow when they occupy an atom. Okay? The first rule I guess we'll talk about is known as Pauli's exclusion principle. Pauli's exclusion principle. All these, by the way, are just named after the person who discovered them. Another thing about today's lesson that might help it sit easier is to keep in mind that, and this goes with a lot of chemistry things and science things, scientists didn't make the atom this way. The atom is this way, and we just discovered it and gave names to it. Okay? So if you have problems about why it is the way it is, then you're going to have to just take that back to whoever you believe made the atom in the first place. Because that's just the truth of the matter, right? Scientists didn't build the atom. We just discovered it and how it's put together. Okay? All right. Pauli's exclusion principle tells us that an orbital can only hold 2 electrons. That's why I picked bunk beds for my analogy, right? Because a bunk bed can hold 2 people while keeping it, rated G. Okay? Now, these electrons also have to have, according to Pauli's exclusion principle, have opposite spins. And must have opposite spins. Meaning, 1 electron sleeps on the top bunk, 1 electron sleeps on the bottom bunk. Now, when we talk about this spin thing, to kind of give you a visual, okay, electrons spin around the nucleus kind of like how the Earth spins around the sun, right? Not only is it orbiting, but it's also rotating. And that's what the electrons do as well, right? So that's another problem with these models is, so they go like this, but then these individual little things are also going like this as well, right? Lots of movement going on. Now, when we draw orbitals, chemists are very simple artists. So if you're not an artist, this is the right place for you, because we don't draw fancy things. To draw an orbital, we draw boxes. Okay, so an orbital is a box. Okay? Electrons, we draw as half arrows, like so. Half arrow meaning they only have like one side of it. Now, technically, if you wanted to, you could draw them as full arrows. We sometimes do that in general chemistry because for some reason people get really like freaked out by half arrows. But that is the most correct way to do it, is with half arrows. Okay? So this is what Pauli's principle tells us. 2 electrons, you can't fit 3, right? So this would be, you could never have like this. That'd be a big no-no. Can't have 3 in an orbital. Okay? Notice it says, like it should be up to 2, so you could have 1. The bunk bed doesn't have to be filled. You can't overfill it. And then the other thing that can't be is you can't ever have them spinning in the same direction. That wouldn't ever happen. They always have opposite spins. Keep in mind, what's the charge of an electron? Negative, right? When you put 2 negative things together, they repel, and that's what causes their opposite spinning. So, okay, questions so far on Pauli's exclusion principle? Yeah? Doesn't actually matter. Yeah, good question. Yeah, so if there's only one, it could go up or down. Yeah. Okay, now, just hang on for the ride, okay? Today's lesson is kind of like I'm throwing puzzle pieces at you, and I promise we'll put them together. So for those of you whose eyes are starting to kind of like freak out at me, take a breath. It's fine. It will come together. Okay, rule number 2 is known as off-bow or off-bow principle. He was German. That's probably not how you say his name, but I don't speak German. okay? His principle or his rule is all about how you fill the hotel. So there's a very particular order that you follow, and it's all based on energy. Okay, so the orbitals are filled by increasing energy. Meaning you don't fill up the 7th until you filled up 1 through 6. Okay, they don't just go to higher energy levels. They always start at the bottom and builds up. Okay, it's often nicknamed the build-up principle, right, because of that idea of always going. Okay, the pattern that we follow, this is a big takeaway from today. The pattern for Aufbau's principle is on the periodic table. The periodic table is your map for everything that we talked about today. And that's the big takeaways. If you can use that, it takes away anything you feel like you have to memorize, which we don't want to memorize things at all. Okay? Okay, that's the Aufbau principle. We'll come back to it here later. The third rule is known as Hund's rule. Hund's rule tells us that electrons are placed in degenerate orbitals before you start filling up the rest. Sorry, I'm getting really low on the board. This is hard to write. With parallel spins. This word right here means that they have this same energy. Can anyone tell, is my screen, can I write this low? Is it still on there? Okay, sometimes I tip it up too high. Okay, so Hund's rule in terms of a visual, okay, would look something like this. Now, degenerate orbitals means that they have the same energy. Okay, so when orbitals have the same exact energy, we connect the boxes together. So this would be an example of 3 orbitals with the same energy because they're all connected. Okay? For example's sake, let's say I only have 4 electrons that need to be placed into this orbital. Technically, if this is it, how many could it hold? It could hold up to 6, right? But if I only have 4 to put in, according to Hund's rule, the way they will occupy that orbital is like this. Parallel spins first. So parallel meaning they're all going the same direction, so up, up, up. Or you could go down, down, down. Then the 4th one then shares. What you wouldn't see would be something like this, where they pair up, but you still have an empty orbital. Okay? So that would never be a thing. As well as you wouldn't ever have like, let's draw one more example here. Like up, down, up, right? That wouldn't ever be a thing either because that breaks the idea of a parallel spin. Questions on what's acceptable and what's not so far in terms of like our pictures that we'll see. Okay, I'm going to erase erase all this. While I do that, everyone stand up. It's third period. You need to stretch, I can tell. Stand up. Rise. While I'm erasing the board, turn to your table buddy and tell them what was your favorite cartoon growing up, or maybe still. Okay, have a seat, everybody. Okay, I forgot something to add to our designations up at the top. Okay? Energy levels in our configuration are signified by numbers. Okay? Subshells, our rooms, are designated by a letter. Now the numbers go in order of 1, 2, 3, 4, 5, 6, 7, and so on and so forth. The letters, though, are very particular. There's 4 types of subshells that have been discovered. There could be another one day if they keep building atoms, who knows? Okay, but the 4 options are, there's S subshells, there's P subshells, there's D subshells, and there's F subshells. Now, these subshells are a very particular size. So all S subshells are the same size. All P subshells are the same size. So on and so forth. The difference is they might be on different energy levels. So for example, the 1S subshell would be represented by a single box. Because the S subshell is only 1 orbital. Okay? Once again, it doesn't really matter that it's a 1 for now, but the S is only a single orbital. The P subshell has 3 orbitals, always. The D subshell has 5. Orbitals. Which means how many electrons can dwell in a D? Up to 10, yeah, very good. And then, anyone see a pattern here for our next letter? Good, yep, so the F would hold up to 7. 1, 3, 5, 7. So the F sublevel is very, very large, right? And could hold up to 7 electrons in it. Once again, we connect them because they're all the same energy value. There's just lots of different bunk beds in that room. Right, so once again, according to our analogy, this is like one giant room with 7 different bunk beds. The bunk beds in the room don't differ in energy. They're all the same. Okay? All right, so with our atom hotel, okay, let's talk about the pattern of how they fill. Okay? Yeah, Evan.
So does that mean like, or like on that example,
yeah,
all the circles would be like different sizes? Because some might be like S's, B's, or
yeah, kinda.
Okay.
Kinda. Let's build off that. So like this right here represents the first energy level, right? On the first energy level, there's only 1 sublevel, and it's an S. Okay, so on the first energy level, we'll just put level 1. It has 1 sublevel, or subshell, which is an S. So yeah, within this ring, is a single orbital that can hold 2 electrons. On the second ring, though, the second level, it has 2 subshells, an S and a P. So yeah, that's where the model keeps falling apart on us, because on this ring, that's not just really a single ring. It's like there's 2 separate rings of different sizes. There's an S one that's smaller and a P one that's bigger. So based off that, and then how many electrons can dwell on the second energy level total? Think one more time. So we have an S orbital and a P orbital. So how many total electrons?
Oh, 8.
There you go. Good. Yep. So this could hold up to 8. This is why back in like junior high, when you draw these pictures, they tell you and say, hey, only 2 electrons can fit on the first energy level. Now this is where they withhold information on purpose because it's way above you. But most of the time, anyone know how many, or we're told how many electrons can be on the third ring? Most of the time people say 8. False, actually. It's more than that. Because the third energy level has an S, a P, and a D. So it can hold up to 18.
So why did they tell us 8? Like, I feel like 18 is just another number, you know? So that's a little weird.
The reason with the 8 is because when you start looking at the ones that are truly valence, meaning the farthest out, it is 8. But if you're talking about the third energy level as a whole, it's 18 do dwell there. But 8 is like what's considered the valence and stuff. So yeah, kind of, it's like one of those, the octet rules, often what they talk about. It's really more of like an octet guideline. Like 8 is significant, but it's not what's really happening. So, okay, we're gonna play a game of I Spy. You ready? First one to find it gets 3 smiley faces.
Oh, shoot.
Okay?
Oh, shoot.
I spy somewhere in this room these 3 number patterns.
There.
Where?
On the right side of the periodic, on the.
These little black numbers. Very good. Have to show your photo. Did you see it earlier? Or you were wondering?
I looked at that earlier.
Yeah, so if you look, notice 2, 2, 8. Now this is interesting. It goes 2, 8, 8 because at this point on the periodic table, the third energy level is not filled yet. But then when you come down to this spot, the third gets filled up to 18, and the fourth now has 8. So how many does the fourth one hold? Up to 32. But it doesn't get filled all the way until you get down here.
How do they know the numbers for the manual one?
We do? Well, these ones we'll talk about belong somewhere else. These ones in a sense it's the same. Like, we know the pattern. I don't know why they didn't list it. That is interesting, huh? Why they chose to stop listing it? Yeah, because it's just the same. Like, we know they're electrons, but, I don't know, we got lazy. Forgot that part. Okay. Okay, energy levels, sublevels, S and P's. Okay. So you can write this down. So the fourth shell, or the fourth level, has S, P, D, and F, which is why it can hold up to 32. Now, technically, the 5th, 6th, 7th, which is as big as we get right now with our periodic table, they all hold up to 32 or more as well. It's just that thing of an atom has room for more. We just may not be filled that big because of the biggest atom we've built. Okay, it's kind of the same reason why the biggest energy level right now is 7. But that doesn't mean in your lifetime we won't see an 8th energy level come up. Particularly because of where the periodic table stops right now. If they make an element 119, according to patterns, it should fit right here, which brings on an 8th energy level. So keep in mind that They exist, they just might not be filled yet. Right? They're just empty rooms in a hotel. Okay, now let's match this to the periodic table. Okay, and that's what I have drawn up here. I apologize, I should have done this beforehand, I didn't think about it, but last period asked. I'm going to get you guys some blank periodic tables that aren't laminated. Your laminated ones are coming. That if you want to color it or label it in any way, you can. But if you want, a lot of people took a picture of this before they left. If you find it helpful, you're welcome to. Okay? But the periodic table is built or organized to follow this, which is crazy. Because we discovered this way later than that was put together. It's nuts how organized this thing is. Okay? So, these first two columns right here are all part of the S rooms, okay? This is the 1S room, this is the 2S room, 3S, 4S, so on and so forth. Now notice for orbital sake, helium belongs in this S grouping. So think of it over here on the left, okay? All right, this right here is the D block. This is the P block, and this is the F block. Now, how many rooms did we say, or how many electrons can be in a P orbital? 6. Notice the squares. 1, 2, 3, 4, 5, 6. Okay? Once again, don't memorize the numbers because it's here to show you, right? I guess you do have to know which one's S, P, D, and F, right? Same thing, D can hold up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Now, when we fill our orbitals, we're going to read the periodic table like a book. Left to right, and then go down. Or another way you could think about it is you have to go in numerical order. Like the blue atomic numbers, you have to go in order. If you go out of order, you're skipping electrons. Okay? So, let's go down to our first example and start putting this weird puzzle together. So we're going to write the electron configuration for hydrogen. The most simplest element there is. Okay, how many electrons does hydrogen have? 1. How do I know that, Isaac? Yep, just that blue number because they're neutral, right? If it wasn't neutral, we'll get to those examples later. Have a smiley face, Isaac. So we just have 1 electron to place. Okay? I'm going to write, I think your table's in the opposite order, but I'm going to write the configuration first. And then we'll draw the diagram. So if you want to relabel your boxes or just make sure you write them in that other order. Okay? All right, so the configuration is going to designate where this 1 electron is located. Okay, well, if I go to my map, this little square right here is hydrogen. So the first thing I do is do the floor. So I'm on the first floor, so I write a 1. The next thing I designate is the room, which is an S. How many electrons are in that room goes as a superscript up top. Okay, so this tells us the energy or the level. This tells us the sublevel. And this tells us how many electrons. Keep in mind, this is not a mathematical operation. It's a notation. Okay, we're not gonna do math with these numbers or anything. It's just telling us information. The way we read them is you would read this as 1s1 is how you would say it. Same thing as if it was like 2, you'd say 1s2. You would never say 1s squared, because squared indicates that you're like doing math on it. So, okay, the diagram is now with the boxes and the arrows. So the 1s orbital is a single orbital. So we draw 1 box. I'm going to label it underneath as the 1s. Then I just put how many electrons are in there, which in this case is just 1. Technically, you could have pointed down. That doesn't matter. Okay, let's do the next one. Lithium. That's the next one, right? Okay, how many electrons? 3. First step, which you kind of just did, we find it on our map, so lithium is right here. Keep in mind, we're reading left to right and then down, so that I always have to start at the top, so the first room that we always fill is the 1s room. How many electrons can be in the 1s room? Up to 2, so I'm going to fill it completely. Okay, looking at my periodic table, there's nothing else on the first row. So I'm going to go to the next row. What orbital comes next? The 2s orbital. How many electrons am I going to place in this 2s orbital? Why just 1, Bryce?
Because there's only 1 electron left.
Yeah, it could hold up to 2, right? But I only need 3 total. Another thing to notice, right, that the powers should add to the total count. Otherwise, you've gone too far, not gone far enough. Okay, drawing our picture, 1s. This time it's filled. 2s needs to be separate because they're not the same energy. And then I put 1 electron in that box. Any questions so far? Okay, let's do carbon. Show me on your fingers for a smiley face how many electrons carbon has. You're showing me 6. Have a smiley face, you're correct. This is 6 in sign language, by the way.
Oh,
In sign language, you can count on one hand. Yeah. It's like one of the few things I remember from high school sign language. It's how to count. But okay, 6. Always start from the first room. What's the first room is? 1s. I'm going to put 2 electrons in there because it's full. The next place I go is the 2s. I'm going to fill that up all the way. Okay, take a look here at my map for a second, everybody. So I fill up this, I fill up this. Now I go across to the 2p orbital. How many electrons do I have left? 2. And so we're done. Notice for a second, everybody, look up here at my map for 1 sec. Okay? If I'm in the 2p and I count over 2 squares, 1, 2, what element is that blank box? Carbon, the one we just wrote it for. Right? So you stop once you get to the element you're writing it for. Okay, let's draw some boxes. So I got a 1s box again, filled. I got a 2s box again, filled. How big is the 2p? 3 boxes big. And you have to draw all 3 because that's how big it is, even if some might be empty. Now I'm only putting 2 electrons in there, so what's the rule? Parallel spins, separate boxes, right? So up, up. Questions so far? Okay, try sodium and aluminum with your table, buddy, and let's see if we're catching on. Ready, set, go. One thing, when you're done with those two problems, kind of to help me know, don't hold your pencil anymore. If you're still working, keep your pencil in your hand. Remembering this, you two? Coming back to you.
That's good, because I get to like pick your brain a little bit, dive in a little bit deeper.
From what we covered before. Yeah. The cool thing that we didn't really get to in general chemistry is we'll start learning in this unit about like why these are even helpful.
I was like, how did I even discover this? Like, what?
Yeah, the discovery of it's nuts, like that side of it that they can.
Like, how did you like see something and be like, that's evidence of this? You know?
Oh no, 20%. Can you last? Have faith, it will last. I don't know if I have a cord. Well, that question. After you finish this, ask that again. Yeah, that one didn't actually bug me for like 3 years. Because well, that's not my goal. But it actually does make sense, and it has a reason. I don't know if you'll like it.
Oh, are we doing a little bit? I was like, I just want to see teacher. That's 13. I feel like we can just like, okay. That's my experience with math anyway. We learned this last year and like, you know, we're doing that.
Keep going. Oh, you two don't. Seeing the pattern, okay? If it feels very repetitive, like by the time you do aluminum, that's a good sign. Because it is an extremely repetitive process, and we'll learn how to simplify it here in a sec.
Just a master's credit for 118.
Well, just wait, right? We're gonna do liver morning before we leave today, so.
Oh, no, that's 160. Ah, shoot. Because it's in
Boxes for days.
It like takes up like 5 sheets of like
So aluminum is where the it's on the table. So it has to be pure. Did you get up to here? Does that all make sense up to there? Kind of. So one thing, yeah, just like Claire was saying, like take it like a map, right? So here's aluminum, right? So we have to go all the way up to 13. So the first one is S, so that should take care of those two, right? 1, 2. We then go to 2S, 1, 2. Then your 2P, 1, 2, 3, 4, 5, 6. So now we go down here, so now we're at 3S, 1, 2. And then we come over here, just read P, stop at aluminum, and that's what I want. So that's why it's 3P, and just a 1. Does that kind of catch in? And if it doesn't all the way, it will come. Because it really is it is a pattern. And I want you to catch on to the pattern. So, okay, I think we're good. I think I checked most, but I'll write them on the board just so you can confirm. You can have a smiley face for each of these you get right. What was the first one I said? Sodium? So you should have 1S2, 2S2, 2P6, 3S1. Questions? Okay, I have a question for you. Let's switch roles. Someone last class asked me, and they had this for their answer. They had 1S2, 2S2, 3S1. Teach them what's wrong there. Yeah, so we skip the P, and so it's not accounting for all the electrons, right? We have 6 electrons that aren't being accounted for. You gotta count all of them, so always go left to right. Another way that will help a lot is you can't skip numbers. Okay, if you're following the numbers on the periodic table, you have to go in numerical order. Okay? All right, for aluminum, you should have 1s2, 2s2, 2p6, 3s2, 3p1. Questions? Okay, let's do manganese. Okay, now, when it comes down to it, especially as atoms get bigger and bigger and bigger, okay, a lot of the electrons in an atom don't, maybe a bad choice of words, but they don't really matter when it comes to what the atom does for us in terms of reacting or not reacting and bonding. The only electrons that are involved in bonding are known as the valence electrons. I don't think we've defined this yet, so if you want to write this off to the side somewhere, if you hopefully you've heard that word before in other science classes. Okay, but the valence electrons are the electrons on the outermost level, and they are the ones that are involved in bonding and reacting. Which is what we care about in chemistry, right? Why do things bond and other things don't bond? Or why do they bond this way, right? How do I make this chemical a certain way so it can do what I want it to do? Okay? All other electrons are known as core electrons. So with our electron configurations, we don't care a whole lot about the core electrons location, because as you noticed before, it just is the same thing over and over again. Right? If we just keep building up, you're always going to start with 1s, and then go to 2s, and then go to 2p. Like, it's very, very repetitive. So what we're going to do is we're going to group all those cores into a shortcut and only list what follows in terms of the valence. So let's write the full one for manganese just to kind of answer Winston's question that he asked that we'll come to in a second, and then we'll talk about the shortcut. Okay, so find manganese on your periodic table. Put your finger on it. All right, so I've got to count all the way up to 25. Okay, so I'm going to start with 1s. There's 2. 2s. 2. Now I'm just reading left to right, left to right. I just have done it so many times, but that's what I'm doing, okay? 2p, 6. What comes after 2p? 3s. Now, you're welcome to draw this or take a picture and use it. Eventually, you won't need it anymore, right? It's kind of like a map, right? You only have to use a map so many times to get somewhere, and then you just know how to get there, okay? Okay, what comes after 3s? 3p6. Now, notice if I stopped here, what have I just written the electron configuration for? Perfect, right? Because I stopped at 18. Okay, but we don't want to stop at 18, so what comes next? Okay, so I've come to here, so I just wrote calcium's electron configuration. Now this is where you're going to have a moment of for a second. The next orbital is the 3D.
Wait, what?
Now for manganese, let's finish and then we'll answer that question. How many is in the 3D for manganese? 5. Okay. Good? Minus the fact that we went to 3? Mm-hmm. Yeah? Okay, yeah.
Is it because it can add up to 18 later? It just does that, but it counts later? Okay.
So, yeah, it's a weird... So what was Aufbau's rule? What did it say in terms of the order we fill? What do we fill by? Increasing energy, not location. So we get this weird thing where the 4s is lower in energy than the 3d. And it's often due because it's so small. Smaller orbitals just take less energy. And so electrons get filled in that before they then actually go back and start filling up the third. That's the second type, but the third. Does that kind of make sense? So that's why we get this weird jump in numbers. The same thing actually happens with the F, but by 2. We don't start filling up the 4F orbitals until we get down to the 6 ring. So when you start getting up to the 6, then electrons start going back and filling up that 4th. Okay? If it helps, there's some weird patterns to help you remember. One of my students came up with the saying of D's are shifted down, right? Because the D orbital, and they're shifted down from what they should be. The other thing is if you count the starting for each, it goes in order. So S starts with 1, P starts with 2, D starts with 3, F starts with 4. So that helps kind of, when you don't have this to look at. But once again, the more you use it, it really will just become second nature that you just know the 3D comes next. Winston, does that kind of ease from when you learned it last year of why that is?
Yeah.
It's weird, and once again, it's just kind of the way the atom is built. In that, I think of it kind of like an onion, right? Because it's full of layers, and we go to higher layers and then lower layers later. So, okay, so let's shortcut this. Now, the rule for shortcutting the core electrons is you go to the nearest element that is completely filled. The only filled elements are known as the noble gases, and they are in this column over, column 18. Okay? So, for manganese, argon is the farthest filled noble gas element, so that's what I'm going to shortcut with. So instead of writing all this, I can just do AR in brackets, which takes care of all of that. Then I just start after argon, 4s2, 3d5. So this is your answer instead of that. Yeah, Kimberly.
Why don't they just keep the last one? Like, just keep the 3D5? Because you would know where it was in the periodic table with just that.
So the whole thing is, it's the information that it's giving us, right? This is telling us the valence electrons in the atom, and these S's are actually still part of that valence section where they can still behave in the bonding process. So, good question though. Any other questions? Okay, let's do one more shortcut together. Let's do silver. Okay, so find what element would be my choice for shortcutting silver. Good, so krypton would be my choice, so I'm going to put Kr in brackets. Okay, which means I get to start here, right? Am I in the right spot? Yes. Okay, because krypton is this box, so 1 through there, we don't have to think about. So the next thing I'd write is 5s, 2, followed by 4d, count over to silver, 9. And you're done. Much better, yes. You may always use a shortcut here on out. Any questions right now? Yeah, Mina.
How do we determine what elements we can shortcut from?
Like this thing?
Yes.
So you always pick the element prior that's filled. So that's this last column. So it has to be
Oh.
one of these ones. Because those ones are totally filled, so none of those electrons are valence.
Okay.
So, good question. Any other questions? Okay, try the next two with your table buddy. If you finish those two, here's your other bonus. Do livermorium after you do those two. If you can do livermorium correctly, it doesn't get harder than that.
It is in like, yeah, 6, then it would be, everything is
It's alright.
What did you do?
Okay. That makes sense. But, so then it's 5, so you said the arrows are jump down. And it jumps right. Jumps right here.
Is that gonna only be like a 5 because like we'll be disrupted on the calculus. It's just
Because the purpose.
But before you go there, you have to go through the entire net, right? And then yeah, that's why I like this one for untrained configurations better than that one. Because that one is confusing because they put the like marker blocks in the spot of the D. That's not actually. Yeah, good observation.
Four is included.
No, it would be, yeah. And LA is just yeah, well, so it is next to the BA, but there's that little LA that's below, so I know that's below it, but it's after the one.
I just realized, are you just the other day, all of a sudden I like saw your last name on here, and I was like, wait a second.
Yeah, I saw it.
It'd be F though.
So, no, it's not.
Oh, wait, yeah.
Okay, so we got into here, right? So go in numerical order. 56, the next thing you go is 57, yeah. Which is actually where we wanted to be in LA, right? So what order is this?
60.
Oh.
Close, it is L.
So 60, 10,
X
7,
You go from 6S to
Oh, wait. Sorry, I went over to
Okay, all right.
Don't match it. So put this, it'd be like that.
livermorium 3.
Once again, once you do those two, try livermorium as a bonus.
and then 49. I need the colors. Yeah.
Feel bad for yourself,
show R and on the text block, or would it just be part of the
Yeah. Yeah, that's why I picked this one in particular for you guys to look at.
Because it has like
It does a better job than that one does, because since this one like didn't put like a spacer in place of where they should be, so they get put down there, which for
then is,
configurations like kind of like throws it off a little bit. So yeah, no, great
Oh,
observation.
so then I would use this one.
Okay, looks like we're most are there. I think I saw most for LA and U, and they look good, but I'll write them out just so you can make sure. Okay, so for LA, you should have RN in brackets, followed by, oh no, not L, that's the next one.
Oh, I was like, no.
XE in brackets, followed by 6S2, and then 4F1. Okay, uranium, you should have RN in brackets, 7S2, 5F4. Now I want to show you something visually, and then we'll do livermorium. This bottom section of the periodic table, if you're going based on number order, doesn't belong here. It belongs up here, and everything gets shifted over, like so. Watch this. Okay, ready? Everyone, eyes up here really quick while it changes. Okay, ready? Give me your eyes this way. So this is how the periodic table should look according to numerical order. And that follows the map perfectly. So you just got to remember that you have to go, right, from the 6S, go back to the electron view, over to the 4F. Make sense? Okay, so for livermorium, where are you, little guy? Oh, all the way over here. Okay. Your configuration should be 7S2, 5F14, 6010, 7P4. Questions on that?
So
Yeah.
how would the columns work? Because like here we start with 4 instead of 3. The fourth column over. Do they go in the third one, or does that not carry over all of again?
Oh, like, oh, I see. Would you, like, are you saying, like, is this the third column?
Yeah.
No, yeah, so in terms of columns, these in a sense are like their own separate columns, technically.
Why are
But,
those so weird?
say what?
Why don't they fit in with the rest of the periodic table?
Like, why did they pull them out?
Yeah.
From what I understand, it deals a lot with, like, chemical behavior and family groupings. That they just pull them out in terms of that. But, and besides, it also fits better on a piece of paper. I'm not sure. Because that obviously fits easier than this. But yeah, so yeah, great question though. Yeah, so off that, these two right here, everyone, make note, these are not noble gases. You can't shortcut with these. Because they're not technically the end of a row. So, any other questions right now? Yeah, Nina.
Your camera's not.
Did it die?
I have no idea.
No, it's not done. It's not done yet.
Wait, it might be still going.
Oh, it's still going. It's just on low power. We're fine though. It can last for what, 5 more minutes? Whew, that's close. I might just recharge it.
If you were configuring like 118 and you were using the shortcut method, does it count as a no?
Oh yeah, good question. So kind of in general, she was asking me here, like if we need to write a configuration for any of these really, you can't just put them in brackets and be done. Right, so if I was doing radon, you can't just do RN, here's my answer, but you can shortcut the one prior. Because the whole point once again is, and we'll see this because we're going to apply this the next few days, like why these are invaluable to us. is the information of those valence electrons is what we want to see here. So, any other questions? Now, one of my not so favorite words, but we'll say it all the time in chemistry, is exceptions. You've just learned the general rules for writing electron configurations. But there are always exceptions to the general rules in chemistry where they don't follow what you expect them to follow. Now, the nice thing about AP Chemistry, though, is according to their curriculum, they don't expect you to memorize the exceptions. But if shown an exception, you should be able to explain why that's happening. So that's what we want to focus on, is don't memorize which ones don't follow the pattern. Rather, why it's maybe doing it that way, so we can explain it. Okay? I'm worried I'm going to get like halfway through and then the bell's going to ring and that just... And then we have a weekend. Okay, we're going to pause and learn about the exceptions next time. Okay? So...